Welcome to week 5. My name is John Posada and I'm an assistant professor at the Department of Biotechnology in the TU Delft. This week we will cover the principles and methods for conceptual process design and sustainability assessment with some examples for the PDO case. Let's first understand why process design and sustainability assessment are important for industrial biotechnology. The ultimate goal of any bioprocess design is to reach an integrated concept that is technically and economically feasible to be implemented at the commercial scale in a sustainable manner. The process design should provide information about process units, operating conditions, process streams, and utilities requirement from the feedstock to the final product at the expected quality. The successful development of a bioprocess takes place along 5 different stages. Concept development, where the scope of the project is defined and general questions are asked. Some examples are: what is the target product and why? And what is the scale of the process? So knowing your potential market is important. We should also ask questions like how this process could be produced or how this product could be produced, and what are the current and promising technologies. So knowing the technological context is quite important too. The next stage is proof of concept, where those initial ideas are experimentally tested to confirm if the concepts actually work. We can now move on to the process design, where multiple processing concepts are generated and assessed through flow sheeting, mass and energy balances, techno-economic evaluation, environmental impact assessment, and even in some cases, social impact analysis. At the end, an integral sustainability analysis is also possible. At this point, we would be able to check if those concepts are technically and economically feasible, and if so, we can proceed to the more rigorous modeling and simulation and check again if the process is still feasible. For those promising concepts, piloting is the next stage to confirm, if necessary, adapt the model's results from the previous design stages. If the process is still feasible, we can proceed to the final stage, large-scale implementation for commercial production. But this is not a linear procedure. There is frequent feedback between the different stages, and as I often tell to my students, process design is a highly iterative activity. So this week we'll focus on how to do process design. Along these 5 stages, multiple initial ideas are discarded, and it is quite normal to start with a couple of hundreds of concepts in the whiteboard to then consider just a small fraction of them at the process design stage, usually around 10 concepts, to then select a few for piloting, around let's say 2 or 3, since it is a cost-intensive task to finally get to one process concept for large-scale production. Multiple decisions are made along these development stages, and designs are always susceptible to changes, especially at the early stages of development where designs are more flexible. Any adaptations in later stages would result in higher cost. For example, early on we may consider other feedstocks or bioreactors, but this is not really possible at the piloting scale stage, where only minor variations in the processing conditions would be possible. For this reason, process design is crucial to provide data for decision making and to bring together knowledge from fundamental science with market and social demands from an applied research perspective. However, this intersection between knowledge transfer and fundamental science with market related and market demand is a well documented bottleneck known as the innovation valley of death. This is where novel concepts are already sufficiently developed for fundamental science, but knowledge is still insufficient for direct scale-up and large-scale implementation. This leads to an inefficient use of resources and hinders the potential implementation of promising technologies. However, this gap can be bridged through collaboration and applied research, where process design is central. So, bioprocess design is important because it provides a systematic approach to provide data for decision making and timely feedback for R&D to steer efforts. For example, engineering a bacterial strain with a higher tolerance to products, and all in all, bioprocess design can help to maximize business success for implementation and reduce overall investments from the R&D activities to the final commercialization. In a similar way, sustainability impact assessment offers a rational framework to guide decision making by simultaneously considering economic, environmental, and social dimensions of the novel bioprocesses and technologies. However, bioprocesses are not isolated entities. They exist within a complex and context-dependent supply chain where multiple actors with specific interests and responsibilities are involved, and they will be impacted at different levels in the three dimensions of sustainability. For this reason, sustainability analysis should consider the breadth and complexity of the supply chain and at the same time the depth of the technical aspects of process and equipment design where different scales of magnitude and time are integrated. For example, activities in the supply chain like interaction among actors and material flows occur at the macro scale in the order of months. The production process itself is a mesoscale system where operation may take just some hours or some days. And in the case of equipment, physical and chemical phenomena like mass and heat transfer or kinetics could take some hours or days. And these processes are at the meso and micro scales. And finally, the actual bioconversion is the fastest process occurring in the smallest scale. As you may have noticed, bioprocess design is a transdisciplinary task that integrates concepts, principles, and methods from multiple knowledge domains and across different scales. Some of these elements have been covered in previous weeks, and in particular this week we will cover how to do bioprocess design. And we will go deeper in the 5 steps of process design as you can see them in the slides. Thank you for your attention and see you in the next lecture.